My name is Alexander Fedulov. I work as a solutions architect at Ververica. And in the line of my work, I'm frequently asked by our customers to help them with various issues that they face when running Flink applications in production. Today, I would like to share some of my experience, hopefully give you some useful hints and a mental framework that would allow you to better approach problems that you might face when running and scaling up Flink deployments. Before we dig into the details, let's establish what is the scope. Debugging is the process of finding and resolving defects or problems that prevent correct operation. When we are talking about issues with streaming applications that prevent correct operations, we need to discuss two categories of problems. Problems with correctness and problems with performance. Generally speaking, problems with correctness is something that is directly related to your implemented business logic. No one knows better than you what your application is supposed to do. So although there are some common pitfalls, it is not very easy to generalize recommendations so that they are applicable to a broad audience. Whereas with performance, we can discuss more general guidelines that are specific to Apache Flink, and this is what we are going to be talking about in the next 30 minutes. Problems with performance are exacerbated by the fact that streaming applications are long-running programs that typically require reservation and pre-allocation of a certain amount of computing resources. But at the same time, the characteristics of the input data and its amount can change at any moment. Some issues can be caused by reaching the natural limits of what is possible at provided capacity. For instance, longer checkpoint durations can ultimately lead to checkpoint timeouts. Backpressure at a bottleneck can gradually degrade the throughput of your application and ultimately maybe completely fail it, and so on. That's why it is critical to distinguish between genuine issues with the implementation as opposed to hitting resources limitations. But first, you need to understand if something is wrong with your application. Therefore, we need to talk about monitoring. Evidently, without it, you might not even spot if there is a problem, but in debugging context, it has additional importance. Debugging often involves changing code or execution parameters. Being able to compare with historical performance is the Ariadne's thread in the labyrinth of decision-making. It makes it possible for you to look back and understand holistically what is the impact of the changes that you introduce. Moreover, some problems can even be directly suspected or identified by just looking at the collected metrics. For instance, imagine that we see that our Flink job stopped outputting data, whereas we're sure that there is new data that is coming into its sources. Because we created a dashboard that uses Flink's metric system to collect the latest watermarks per subtask, we can immediately spot that something is wrong with one of them. One of the subtasks seems not to have a proper watermark. This typically indicates that one of the source partitions is idle, and this needs to be mitigated by either with an appropriate watermark strategy or with a custom watermark generator implementation. In general, there are some very useful high-level metrics, such as the number of failed checkpoints, the number of application restarts, etc., that are worth putting front and center in your monitoring tools, and in addition, creating alerts for them. On the more detailed level, I can recommend to track details about each checkpoint, such as duration, size, checkpoint barrier alignment time. Checkpoint size is a good indicator for the amount of state accumulated in Flink. Frequently, misunderstandings with regard to how Flink applications are supposed to work arise when people start running Flink jobs, and after some time of stable performance, they think that they are operating a properly sized cluster. but the actual state underneath the application still keeps growing. So at a certain point, such Flink applications might start throwing exceptions, but they're actually caused simply by the fact that you do not have enough capacity to run them for a longer duration of time in the first place. So if you're looking at a window of time of 30 days, for instance, you'll need to wait for at least a representative 30-day segment or bootstrap it artificially to understand what is the state size that you're going to be processing in your app. And obviously monitoring is critical for recognizing this aspect. I would definitely also recommend adding throughput statistics into your dashboards because they can directly help you identify abnormalities or degrading performance. They're useful to establish where you are performance-wise in the normal case and see if anything causes you to deviate from that baseline. As I said, debugging often involves tuning some knobs, and you would like to make sure that by doing so, you do not adversely affect your overall application performance. The same applies to the latency measurements if low latency is a critical aspect for your particular use case. When looking at the throughput, don't forget to correlate it with the rate of events that are available at the input. Another useful metric that deserves a mention here is consumer lag. It shows if your application is able to keep up with the incoming data flow. If the consumer lag keeps growing and you suspect that the throughput might not actually be adequate, the next thing to look into is backpressure. A quick reminder what backpressure is. Let's say a system can process X events per second, and all of a sudden it starts getting twice as much. What can you do? Well, you can either start dropping messages, which is most certainly not desirable, or you can tell the upstream system to only send you X events per second. Backpressure is the mechanism that implements such pushback. This way, data can be buffered somewhere in a persistent channel, such as Kafka. Is backpressure a good thing or a bad thing? Well, it is both. It is good to have it in Flink as a mechanism to prevent dropping messages, but it is not good to constantly have it in your application. If you do, you need to investigate what is the reason. In general, getting into a heavily backpressured state is one of the most common causes that initiates a debugging session into a Flink application. Backpressure is a symptom that can be caused by a variety of reasons. And the best tool to start looking into it is Flink's UI. Over the years, it has become a Swiss knife for debugging issues with Flink applications. And it actually keeps getting better with two significant additions in Flink 1.13 that we're going to discuss in this section. So back to the topic of backpressure. If you worked with Flink prior to version 1.13, you might know that previously, in order to find the source of backpressure, you had to click through the individual operators in the job graph while looking at the backpressure monitoring tab in order to identify which one of them is the source of backpressure. This process got much easier with Flink 1.13 because this information is now directly integrated into the job graph. You can now spot the operator that causes backpressure simply by looking at the job graph. As you can see, the job graph nodes now have different colors, and those colors represent a combination of two factors: under how much backpressure the operator chain is and how busy it is. Idling operators will be blue, fully busy operators will be red, and fully backpressured ones will be gray. Anything in between will be a combination of those two colors. And so now we can right away see that the first two operators in this job graph are backpressured. We can also spot the busy red operator downstream of the backpressured ones. And this one will most likely be the bottleneck that is the source of the backpressure. Despite how useful the job graph-based visualization is, you still might want to go to the Backpressure tab because of the level of resolution. It gives you the details of backpressure at the level of subtasks. In other words, individual parallel instances of the operator. Why is this important? Well, because it can immediately give you an indication that you might be facing a situation related to backpressure caused by imbalanced processing load. If you see a situation like the one on this screenshot, it could be something in your implementation that causes more work to be done for particular keys, or more likely you're facing data skew. Such pattern where some subtasks are backpressured and some are not can naturally arise even if just one of the keys is heavily skewed. How does it work? If you have a key buy between two operators and you have one outlier key with much more data than the rest, its subtask is going to get busy and push back all of the previous subtasks that send data to it. This way, effects of a single heavily skewed key at the end of the job graph could propagate upstream and clog the whole pipeline. To confirm the data skew hypothesis, it is useful to take a look at the checkpoints tab in the Flink UI. In addition to the overall operator statistics, it also displays the breakdown per subtask. In most of the cases, key skew will be also reflected in the corresponding skew of the checkpointed data sizes per task. If you're facing issues with checkpointing, for instance, checkpoints, timeouts, this view is very helpful to get additional insights. It contains the breakdown of the different phases that correspond to the propagation of a checkpoint barrier through an operator. What are those phases? The first phase, going from left to right in the table, is the synchronous phase. During this phase, a snapshot of the state is created locally. And the goal is to create this snapshot that can be later copied to the checkpointing location asynchronously, while at the same time being able to modify the state by the new incoming data. This phase blocks input channels momentarily. And for the hash map state backend, this phase is usually very quick. It's just an efficient operation on the multi-version control data structure that is used, that is backing the hash map state backend. Whereas for RocksDB, this stage involves flushing data structures from memory caches to disk. Everything has to be materialized on disk for further copying. What if this phase is slow? This is mostly relevant for RocksDB. You need to check if the disk performance is adequate. So do you have enough IOPS for RocksDB to finish writing this in-memory data fast enough? And the second thing to keep in mind is you might need to increase the number of RocksDB threads that are responsible for writing this data. By default, there are 2 threads, and sometimes it is beneficial to increase it to 4 or 8 threads and see if it gives you performance benefits. The next phase is the asynchronous phase. During this phase, the previously created local snapshot is being written to a distributed file system. This process happens in parallel to processing new events. What if this phase takes too long? So first thing to consider is the performance of the external file system. Is your distributed file system fast enough? Or maybe even, is it potentially throttling your writes? Some systems implement requests per second throttling, so they don't allow too many parallel requests. In this case, it might be beneficial to, in order to verify that, to maybe temporarily even decrease the parallelism of your application to have less parallel outstanding connections. And the second helpful thing is to increase the memory threshold parameter. This threshold parameter determines how large is the checkpoint data chunk supposed to be in order to become a separate file. Everything that is below this threshold is going to be inlined into the metadata file. And this metadata file is written once by the job manager. And so therefore, if you have a very high parallelism and using incremental checkpoints where maybe just a couple of keys get updated between the checkpoints, instead of writing thousands of separate files, you would be writing just one metadata file, which is going to significantly decrease this number of requests per second outstanding to the external system. The next thing to check is if your network performance might be a bottleneck to upload the checkpoints. And in case of RocksDB, there's another parameter, which is number of threads used for uploading the data. This parameter was 1 until 1.12, and it actually was increased to 4 in 1.14 by default. So if you're using an older version, you might also go ahead and increase this parameter. It might be helpful for your overall performance. The last stage in the table, but it's actually the first stage that happens when the checkpoint barrier arrives, is the alignment phase. This is the phase when an operator that has multiple inputs waits for receiving the checkpoint barriers with the same ID on all of its channels. If you have long alignment phase, this is an indication potentially of skewed backpressure, because some of the channels are backpressured and some not. So you receive and the checkpoint barrier travels together with the data. So it means that you will receive this checkpoint barrier faster on the non-backpressured channel and will have to wait longer on the backpressured channels. If this is the case and you observe non-stable performance, it might be useful to consider using unaligned checkpoints. Unaligned checkpoints, in contrast to normal checkpoints, contain in-flight data, that is, data stored in buffers as part of a checkpoint state. And this allows checkpoint barriers to overtake these buffers and, in essence, reduce checkpoints durations at the cost of increased checkpoint sizes. And this brings us back to the topic of backpressure. What else can you do to mitigate it? Well, if you're dealing with backpressure caused by the key skew, you can try to work around this key skew. You can do this by either using a different key if it's possible, or alternatively construct a solution based on some sort of a multi-staged map-reduced style processing with an artificial composite key. You can append some entropy suffix to the key values. By doing so, benefit from processing data in parallel, and then reassemble the parts for the final result. This might or might not be applicable to your use case depending on the calculations you perform. If during your debugging analysis you come to the conclusion that your pipeline is not backpressured because of the key skew, but you simply cannot process the input data fast enough, the right thing to do is scale up, add additional resources. When you do so, make sure that you scale up all resources accordingly. So if you're using RocksDB as your state backend, you need to make sure that you also gain additional IOPS. And after you scale up and your application runs stably, you will probably be interested in understanding which parts of your code might have been the bottleneck. And this leads us to the next chapter of the debugging journey, which is profiling. Profiling makes it possible to get deeper insights into the inner workings of your code and capture details that are not available elsewhere. There are a lot of great profilers for the JVM, and all of the best practices for profiling Java applications apply to Flink. The question that comes first is, how do you attach a profiler? There exists a possibility to add the options listed on this slide to your Flink conf YAML, and by that enable attaching a profiler to the individual task or job managers remotely. However, a proper setup requires authentication, SSL certificates, and so on. And chances are you do not have that in place, and enabling unsecured JMX connections to production environments is never a good option. Luckily, you typically do not need to resort to that. While debugging on an existing cluster is possible, it is often easier and more beneficial to perform local debugging first. With a representative data sample, inefficiencies in the code are going to manifest themselves either way, but local profiling has a lot of advantages. It allows faster iteration on changes. It is closer to a development environment, and there's no need for a complex setup. So my recommendation, if you think you need to attach a JVM profiler, is to do it locally first. We started talking about profiling as a means to identify bottlenecks in your code. And with a lot of different JVM profiler options, some of them are more convenient to use than others. But typically, if you use a profiler to understand where your application CPU memory resources are spent, you're presented with a view similar to the one in the screenshot made with Visual VM. What you see is the distribution of time across different method calls spent on the CPU. This view is helpful, but such representation has two main problems. It mixes both actively running and blocking calls. So you have a mix of something like this epoll wait method and at the same time some useful calls that belong to your application actively running on the CPU. The second problem is that it does not give you an understanding of how exactly you arrived at running a particular method. So maybe there are 20 different code paths that could lead you to running a particular method in your application, but you have no idea how you arrived there. In order to address those limitations, a special visualization called flame graphs was developed. A clarification right away, the color scheme has no real meaning, it is just there to make flame graphs look cool. Let's take a couple of moments to understand how to read flame graphs and why they are useful. For that, I'm going to use slides by Brendan Gregg, who came up with this visualization. The link to his in-depth presentation is below. Flame graphs are constructed by collecting a number of stack traces samples and consists of such bars that are associated with the method calls. The length of each bar is proportional to the number of times it appears in the samples. The way these bars are placed is such that they preserve the ancestry. So if a method C calls a method E, then E will be put on top of C, and so forth. This visualization makes it possible to answer some questions easily just by looking at the graphs. So you can, for instance, visually compare the length of the bars and understand that 90% of the resources go into executing method B and its descendants, and only 10% of the CPU is busy with things related to the call to G. It also shows you exactly which methods are actually directly executed by the CPU. So if you look at the bars at the very top of this flame graph, these are the actual methods that are using your CPU cycles. And also we can answer why is a particular method running. So if you go from bottom to top in this example and encounter splits that you know represent branches in the code, like the one here, for instance, you can conclude that the method f at the top is running because A first chose path B and then method C chose path E. So it is easy to understand how you actually ended up running the method f. And the coolest part is that also since Flink 1.13, the flame graphs visualization is available directly in the Flink UI without having to use perf or other tools, which would be tricky in a distributed system anyway. The sampling process is pretty lightweight because it is based on basically collecting just some thread info statistics, but to be extra cautious, we decided to put it behind a feature flag for now. You simply need to enable them in your Flink config by specifying this parameter. Another cool thing about flame graphs in Flink is that you can view blocking and non-blocking calls separately. So on CPU, flame graphs only include samples of threads in runnable and new state, and the off CPU flame graphs contain details about the blocked calls. The final thing I would like to mention is that if after all of the debugging and profiling you performed, you still cannot localize the issue, you might need to dig deeper into the logs. And here it is useful to remember that Flink is a modular system, so instead of flipping a switch and enabling debug on everything, it is advisable to first find packages or classes that you suspect might be related to the issue at hand. And here I gathered a couple of examples from my experience that came up several times. The checkpoint coordinator class is helpful to get details around the checkpointing process. It also prints checkpoint statistics, which could be especially helpful if Flink UI is disabled. The literal action package is relevant for issues with high availability and job manager failover. S3 Hadoop and S3 Presto packages can be useful for investigating issues around writing checkpoints, save points, and cleaning them up. And also everything that is related to interfacing with the external DFS systems, such as, for instance, issues around multi-part uploads. In conclusion, Flink is a complex distributed system and debugging it is not a trivial task. Luckily, there are tools available that make this process easier, and Flink's community is constantly working on improving the existing and adding the new ones. I hope that my today's talk gave you some useful hints on how and when to use them. Here are some of the key takeaways. Proper monitoring is a prerequisite not only for spotting issues, but also as a primary navigation device on your debugging journey. If you face issues, you should generally approach them in the following order. Look at the detailed metrics. Try to spot issues that lie on the surface. Continue with the Flink UI, including the backpressure and checkpoint monitors. Also check Flink UI for any root cause exceptions. If you were unable to understand the problem or find the solution, or maybe you simply want to optimize your code, continue with profiling and flame graphs. If you still need to go further, there are also some more advanced techniques available, but they will most likely require you to get intimately familiar with the implementation details. And this is why we all love open source. I would like to thank you for attending my today's talk, and I'm now happy to answer your questions.